Alright, welcome back, Physics 30. Today we're gonna learn two lessons actually. I generally do one lesson at a time, but lesson number 3, reflection, basically take least of the time. It is recalling of what you learned in junior high science when you learn about reflection or light property. However, what we are going to do is reflection and refraction. Some of you guys may know that refraction, I already know it's a bending of the light or bending of the wave, but we're going to learn a little bit more detail. We're not going to go to a really in-depth mathematical equation. If we have a chance, we'll get to something I like to call it as Snell's law, which is definitely related to a bunch of different mediums and refraction situations. So let's get this started. Reflection. Reflection. When it comes to reflection, it applies for both particles and waves. Think about it in this situation. You're tossing a rubber ball towards a wall. Then you may notice that after hitting the wall, it's going to reflect back. Wave, think about it in this way. Imagine you're facing a wall and imagine the audience are behind you. You're saying and yelling something towards the wall. The funny thing about the reflection of wave is audience can hear that clearly. It may go a little less volume than when you're facing the audience, but you got the idea. Long story short, particles and wave have ability of reflecting whatever that is going into. We call it incident. And after that, reflected, we're going to get the same result. We're going to talk about in terms of wave most of the time, which is the reason why we're breaking this in a part 1 and part 2. Part 1, we're talking about light as wave. So here's what happened. Oh, before we get things started, we need ruler for today's lesson. So, technically, what is it called? Your protractor can be useful too, but ruler is mandatory. Protractor if you want. First thing first, we need to understand a few things. Law of reflection. You guys should learn about this in junior high. Law of reflection. Basically, law of reflection is mathematical explanation that shows that the angle of incident always equals to angle of reflection. One thing that people always do as a mistake is angle of incident. Now I'm going to go to this diagram over that side. Angle of incident always is created between the normal line and incident ray. And angle of reflection, similarly, you are creating an angle between normal line and the actual ray that is reflected. Let's talk about this normal. In physics 20, you guys learn about normal force. Having a normal means it's 90 degree perpendicular. So that's normal angle. This normal line, yes, it technically does not exist. However, when it comes to an angle of reflection, this angle over here, so between incident ray and normal angle, we call it theta I, incident angle, and similarly, mirror image to the other side, theta R, between normal line and angle of reflection. These two are always equal together, and that is what I like to say about this law of reflection. It is just a quick recalling for you guys, and it should be recalling for you guys. Now let's do a quick example. What is the angle of reflection of the mirror B? So I have mirror A over here, mirror B over here. The very first thing that you need to understand is, fortunately, diploma doesn't have a written response for now. So more about theory part we need to understand, and you may not see this type of question a lot. First thing first, it's a good idea to create our normal line. So 90 degrees. You may notice that I'm using my corner. There you go. This angle over here is my angle of incident. It is my incoming ray and normal angle. The way that I get is, well, 90 minus 21. I believe is 69. So once I get the 69, here's your second part. I need to create that much of angle to the other side. That's where protractor can play a huge role, but you can kind of guesstimate too, as long as mathematically it's on the right track. Now this incident angle turning into reflected angle. Sorry, incident ray will now turn out to be reflected ray. And that is my 69 degree because it's my reflected angle over here. You may notice that this angle that I have inside will be 21 degree. This is one of the reasons why people try to connect that, oh, Mr. Kim, in the end, even if I'm not looking at incident angle and refracted angle, I can just write 21 to 21, isn't it? To be fair, it is correct. But theoretically, you should still understand that law of reflection does not discuss about the surface and the radiation. It is actually radiation and the normal line. And we have 76 degree. Now after that, we're going to do basically the same thing. Having normal line and things should be reflected again. So now this is incident and now this is reflected as a second situation. But here's a problem. We don't know any of an angle. Now in that case, we gotta use this geometry triangle. It's an obtuse triangle. However, we can figure out that angle over here. It's 180 minus 76. So 180 minus 76 gave me 104 degree. And I can actually find out how much angle that I can create for this mirror surface B and the incident angle on my second radiation. Now the way that I can use is basically subtract from my total angle 180 minus 104 minus 21, which gives me 55. Now be careful. The question is asking angle of reflection. So it's talking about this angle specifically. Which means you will know that this basically 55 degree will be identical to the other side between the refracted radiation and mirror side B. So now what I need to do is 90 minus 55, which is 35. And at that situation, you don't need to do any other stuff. That will be my final answer. Honestly, this is review situation. Diploma doesn't have that much of reflection really into this situation, nor we don't have written response. However, reflection will come out in a different way. So have that in your mind. Now, some people who watch like movies such as like Mirror and then Virtual Universe, those kind of situation, I like to say it is not entirely wrong. Basically, when you see something inside of a mirror, we call it virtual image. So I'm going to talk about plane mirror situation first of all. Prepare your highlighter. There's not much things to write. It's more about highlighting situation. So first thing first. The image located where the reflected rays appear to be, we use the word converge. And the eye, and think about that as a reflected image. The eye cannot tell that rays have been reflected, and we are assuming that it traveled in a straight line. And I'm going to explain to you what that means. First thing first. And I'm gonna talk about converged image and diverging image later. Converging image is something that we see as real. So if you look at left side over here, I have my eye and I have an actual object. It's a converging image. If it's go other way, that's a diverging part. But again, we're gonna talk about that in detail when we talk about the line diagram and the others. So let's deal with this. So object, basically, let's say, as an example, you have 50 centimeters away. Let's be realistic. 50 centimeter away. Let's say. And it's a plane mirror. When you see those objects, the thing is, our eye actually see an object on the other side of the mirror, which we call it virtual image from this perspective, because it doesn't exist technically. It is an object that is being reflected. But if it's plane, you will have same distance. That's what I want to point that out. If it's plane. If it's not plane, rocky or bended, that's the one where you see in a Telus Worth Science Center, where you see like yourself shrink out, become larger, inverted, those kind of situation. It is not plane mirror, but in this case it's a plane mirror, and we generally use dotted line. That is actually quite important because we are going to use dotted line and solid line to find out which one is real, which one is virtual. So virtual, use dotted line, real, use solid line. So far for today, you just need to understand that they share same distance. Characteristic of reflected image in this situation. You may notice, since it's a plane mirror, whatever the object that you see from the real side in a virtual image, they should share the same size. Your height is, let's say, 6 feet. In real life, when you see through your plane mirror, it should also be 6 feet. Vertically upright, it's a fancy way of saying you're not inverted. If I'm standing, like toes at the bottom, head at the top, same thing should happen. And the image should be virtual. It's not real. You're looking at your probably left-right inverted situation. If you raise your right arm, and technically in your image, yourself is raising your left arm. So that's the only differences. So thus virtual. This is my first half of lesson today. When it comes to your work part, please give it a shot for homework part A and B, all of them. But please don't go to your assignment part now. Let's go to Physics 30. Lesson number 4, refraction. Now, refraction, things are quite tough. Now, refraction. This is a perfect trait for wave. This is a perfect trait for wave. Now, if you guys remember, wave have same frequency, constant frequency. However, speed of certain wave can change. But how can I change that speed? It actually depends on medium. And medium is any type of object that can transfer the wave energy to the others. And any type of solid, liquid, gas, they basically have an ability of transferring wave from one, which is source, to another. And this is the one where diploma question emphasized quite a bit, by the way. Now, and we can talk about anything like sound and light, but let's talk about light. If you shine upon a light from the air to the water, so imagine you have a glass of water and then have a light or laser going through, you may notice that the direction change. So refraction is basically change in direction of any type of wave. And it passes one medium to another and we create a different angle. So let's look at this situation over here. This is a good example. I know it's a little tough to see, but medium 1, let's think it as an air, and medium 2, let's think it as water. The way that you find out the angle, by the way, it's exact identical. Can you see this interacting point between first medium and second medium? I want you to draw 90-degree normal line and normal line. This angle, we learn about this one, delta I, incident angle, it's exact same thing as that. And number 2, which is this angle of refraction for this time. So I'm gonna put REF. So again, we're comparing this angle to that angle. And I'm gonna tell you, these are not equal when it comes to refraction. There are two different situations. How much things are packed, basically. So if you are looking at air and water situation, air is gas, right? Water is liquid, right? Which one is more packed? You may notice that the number of mole in here is actually less. So actually I'm gonna avoid the N. N will be used as an index later, but in any case, less packed and more packed. If you're dealing with a situation where it's less packed, the angle is a bit larger because you have more freedom. If it's more packed, it's gonna get shorter, smaller. So think about it like Boxing Day situation. Imagine you're going to West Edmonton Mall in Boxing Day. You don't have a freedom of choices. You go whatever that tiny path because of swarming amount of shoppers in there. That's this situation. On the other hand, this is a situation where imagine like 10 a.m. Monday where everybody works. And if you happen to go to West Edmonton Mall, you have more path that you can go through because there are not much of people simply. So that's the analogy. Less pack, have more angle, more pack, less angle. Now, to find out these, every single situation, it is a chore. I mean, it's not much of a hard math, it's algebra, but scientists discovered a relationship between medium and they call this relative comparison of index of refraction, and that's when we use N. This is one of the reasons why I was gonna put N for number of mole, but I kind of changed my mind because of that. So if medium changes, the speed of the wave changes, in this case light. So when the light travels slowly through a medium, a packed medium, I like to say, like liquid and solid, we say that medium is optically dense. So again, my logical conclusion that I like to give it to you is more dense means more packed. That means speed of the wave goes down. That's what I want to point it out, folks. To determine the optical density, we use the formula C over V. So technically the highest density that you can think of, lowest density you can think of can be 1. Because C is always higher value. C is 3.0010 to the power of 8. V is speed of the light in a medium. and we don't know what the medium is. It can be liquid, solid, gas, one of those. There is some inverse relationship between N and V, because as you may notice, this is a situation where y is equal to 1 over x situation if you think about it. So inverse relationship. That means if I have higher value of n, then it's more dense, so speed will slow down. When it comes to air, this is 1, smallest value of n that is possible, thus highest possible speed of light is achieved. So have that in your mind. So let's do an example over here. A laser is shone through water and is equal to 1.33. It reflects off a distance object and return in a total time of 183 microsecond. Determine the distance of an object. So we're talking about this situation. Let's draw it first. So I have water and I have distant object. Laser is going through, like, let's try to go straight as possible, but like it's kind of like that situation. But imagine we're doing the angle closest to 90 degrees. Let's put it that way. Then it's going down and up. Now, n value is given as 1.33 for the water. N value for air is 1.00. So we know those two values. And it says the time it takes for the returning time was 183 microsecond. So 10 to the power of -6 seconds. And now we'll try to find out what is my distance over here. So let's talk about each of this situation. I'm going to call this as an incoming 1. This is refracting 2, or initial final, if you will. V1, we know, 310 to the power of 8 meter per second. V2, we don't know. So basically, we're trying to find our V2 first, because we know the time, so V is equal to D over T. We can easily use that combination. So let's talk about our index first. Our N is equal to C over V. We know that if I isolate for V, V is equal to C over N, and the C is speed of light, 310 to the power of 8 meter per second, and N was 1.33. We are talking about the water, so we are finding out V2. Now, that means let's punch some of those numbers in. I have 22556, that nasty number. So I'm going to skip this number in my calculator, but as an expression, it is about that in water. Now, we know our time, which is 183, 10 to the power of -6 seconds. So, if you think about going back and forth, it specifically said it's a returning time. So that means I better divide this time by 2, because it's a total time. So if I divide this thing by 2, it should be about 9.15, 10 to the power of -5 seconds. So we are basically using this speed, that times D is equal to V delta T, and delta D is basically multiplication of those two numbers. I'm going to round it up to my final answer. It should be 2.06, 10 to the power of 4 meter if I use significant digit, or simply 20.6 kilometer. these two. Now, before I give you any type of question for now, let's do a little theory questions too. This is where I summarize refraction part really in detail. Like I mentioned, this is only for the waves, not the particle. Particle rather do reflection or go straight. I talk about density. If you have a situation you're going less dense to more dense. So like I said, example of that can be air to water. Can be ice too, glass, whatever you call, if it's solid. Whenever that happens, know the fact that law of reflection still work. That means my initial theta, incident theta and reflected theta, they basically share the same angle. We know that. However, a big conclusion is my reflected angle should be and must be smaller than my incident angle. So this one is way larger than going out. This is one of the reasons why ruler is needed. Not much of a protractor as much, because we don't know these angles unless we use that mathematical formula again, like what we did. If you go to a second situation, now it's completely opposite. More to less dense. This is again situation, but imagine you're shining something from water to air, something like that. Still, law of reflection works same. So if it's happened to reflect, you know that this angle over here, incident and reflected one, they are identical. However, because it's more dense to less dense, you have more freedom of going out. So what you will see is this angle of incident over here, angle of reflected one, that's way bigger angle because you have more freedom. Again, less dense means less packed, means more freedom for light. My last example, we're basically predicting how things are going, like reflected ray and then refracted and refraction. Sorry, having a little verbal glitch over here. Reflection and refraction, we're going to use both. And it's glass and glass. One is like prism, one is just thick glass. Imagine what you use for the table. First thing first. Normal line. This angle of incident work the same way of going out. These two values are equal together. Now let's think. And generally I tend to draw in a vertical way. That makes my life a little easier. It's your choice, however. We are now going into less packed to more packed. Less dense to more dense situation, which means I don't have a lot of freedom. So make sure the angle that you're drawing should be smaller. Now that's one thing. And again, in order to find a specific angle, we need to use mathematical formula. So let's not talk about that. We're doing qualitative analysis in here. Although I accidentally put a straight line over here, make sure you draw normal line and know the fact that when it comes to refraction, it's always go towards one direction. You go back, that's reflection. Have that in your mind. Now we're going more to less, which means I have to draw, this is my incident angle. As long as I draw a little bigger line for my refracted angle, that is what you need. So in the end, it should look like this. Going with larger angle, smaller angle, larger angle again. And these two angles are actually identical. It's just geometric part. I don't think diploma may go that detailed, but have that in your mind. Now, next part. Like I said, I like to match everything in terms of perspective. So surface line is horizontal. 90-degree normal line. That's my incident angle. It is glass, so there is technically some part of reflection going on like this. I kind of screwed it up, but you got the idea. We're going less packed to more packed, which means angle of refraction should be smaller. So as long as I draw something smaller like this, it's all good. Now, after that, because it's triangular prism, the perspective go a little off. But 90-degree, normal line. Right now, we're having oh yeah, it is. Even though, sorry about that, my drawing looks very horrible, but this is my refracted angle. And as long as I have, from now it's more to less, as long as I draw some angle that is larger, probably, okay, this is a small angle. So let me just draw something large on purpose. There you go. It's definitely larger angle, refracted. And that should be my answer. In real life, if the sunlight coming in and then it go refracted off all the time, you will have rainbow actually, red all the way to violet. So ladies and gentlemen, that is my lesson for today. Your to-do list is solving every question on lesson number 3 and lesson number 4. Do every homework question on refraction too.